pleasure to have Professor Tian from Princeton and Peking University here for the second of the Landau Lecture series. We're talking about metric and algebraic limits of Kähler manifolds.
Thank you. So today and tomorrow I will give two talks to explain certain parts of what I said yesterday, not yesterday, 3 days ago, and so today is a bit analytic. Tomorrow will be algebraic. So actually today's part is concerns this most technical part of the proof of the main theorem I said last time, but I do not plan to tell you all the things because that's I'm short of time, and so I basically try to explain to you why this so-called partial serial estimate comes in. Okay, so and what's the role it plays. So let me start with some general things. So suppose I have a Riemannian manifold. Okay, so suppose in the case I consider the Ricci curvature of G is big equal to some constant times G. Okay, so in the Riemannian geometry, or in at least today's geometry, for example, when we solve a Poincare conjecture, or in other cases, we need to study a so-called compactness theory. Mu is a real number. Doesn't matter. It's just a real number. So we basically say Ricci curvature bounded from below. Okay. So compactness type theorem. Okay. So that means if we take a sequence of say for simplicity, let's take a manifold fixed, but the G is okay. Then maybe there's a base point inside N. Okay, if M is bounded, has a bounded diameter, you don't need to plot this point. Okay, so then we want to see whether there is a limit. Okay, and so this is first, and second, I guess that's so it's all the result of Gromov. And these conditions, by taking a subsequence, if necessary, a subsequence of this converge to something which is a d infinity at the beginning and x infinity.
But then you need a uniform bound on the...
I need a uniform bound, yes. Mu is fixed, okay? So maybe I should specify that with Ricci bounded from below by mu, say. Okay? Okay. So this is in the Gromov-Hausdorff topology. So by that we means this is so this is at beginning is only a metric space. It's a metric space. Okay, so by that we means we invent. So if this M G X I say is embedded in some metric space, Say let's just plot it this way. Okay. So then you can define in this. So the distance between a Hausdorff distance between M and M infinity. Okay. And then you take all the infimum among all the possible isometric embeddings. So you want this to be a 0. So of course you also want to embed this. So this is Gromov-Hausdorff distance. Okay. And there are some other ways to describe that. For example, you can describe in terms of covering and so on. Okay. So this is known under these assumptions. Okay. The things is the question is, the fundamental question is, because in geometry this is a quite a weak space. It's only a metric. It's a length space. It's a metric space, but you can also compute the length of curves. Okay. It's too weak. So what we need is we like to know is what the regularity of this. Of this m infinity and d infinity, and this is just space point. It's not that crucial in this part. And once you have that, you can also ask, suppose this one, for example, this one is smooth. Okay, so then you ask whether this topology convergence is stronger. Okay, so is convergence stronger in stronger topology? For example, CK topology or C infinite topology, whatever. Okay, so essentially it's a regularity issue. Things. Okay, so there is this has a long history of things. For example, in the low dimensions, even when I was a student, I did something. So the general theory, the first really general theory of this was given by Kähler coding. I don't, because of time, I cannot mention everything. Okay, so in the 90s, they proved the following things. They developed a regularity theory. Okay, so at least this implies one thing which is very important, namely is if for any point here, m infinity, the tangent space exists. So what do we mean by tangent space? That means if you take Ri goes to 0, okay, then you scale your space like you try to take derivatives. So you scale your space Ri minus 2, and you enlarge your, and you use this as a base point. And this converge to some another, in the Gromov-Hausdorff sense, converge to a metric cone. Okay. So this is in the Gromov-Hausdorff. So of course you may need to take subsequence if necessary. A tangent cone may not be unique. So you take different sequence may give you a different tangent cone. May give different tangent cone. But the key point is the tangent cone exists. So limit is a cone. Namely, there's a radial directions. In radial direction. So then they can do if you know the better. Of course, in general, you also have some things. To be simpler, let me put the things. If, say, Ricci curvature is constant, say, like in our case, it always bounded, it's Einstein. It's Einstein, okay? Always bounded is enough. Enough, but you need to, you don't get as strong as I'm stating now. So then, and Txm infinity is Rn, namely cone is trivial. Then m infinity is a smooth near x. So smooth near x is nearby is actually diffeomorphic to a piece of Euclidean space. Okay, and the diffeomorphism is C infinity here. Okay, and moreover, this D infinity near this point is a smooth metric, given by smooth metric. Say I write G infinity, that means it's a Riemannian metric now, and also satisfies this equation. Okay. And moreover, you can say the GI converge to G infinity in C infinity topology. It's all nearby this point. Okay, all nearby this point. Nearby X. Okay. Then from here, they further argued. Okay. They further argued. I mean, this is not a straightforward things. Okay, they further proved, plus some other arguments, you can, by looking at the tangent cone, because each time you get a tangent cone, each time you blow up, you get tangent cone, and then you can also study a tangent cone, because tangent cone will also have this property, namely it's also a limit of smooth ones, because you scale the manifold here appropriately. This sequence all can converge to this tangent cone. You can replace M infinity by tangent cone and argue again, repeat arguments. So you can say that you blow up again. That means you get a lot of homogeneity. So by doing this reduction process, you can say you can at least prove the following thing, namely the M in this case. Okay, so M infinity is a smooth. So there is a closed subset and S inside M infinity such that the dimension, Hausdorff dimension, so maybe I put it this way, n minus 2 Hausdorff measure is locally finite. Okay, because I didn't say it's compact yet. Okay, and M infinity, D infinity, S is smooth. And so on, have all these things. So this convergence and the smooth of metrics, or is true outside S. Okay.
What is the subscript on Hn minus 2 of S?
This is Gromov. This is Hausdorff. So
it could, in theory, could be the whole manifold now, right?
It could be in whole manifold. S could be empty.
So there is no, for Ricci curvature bound, there is no theorem like the Otto Shior theorem that somehow you are smooth almost everywhere also.
Sorry, maybe I repeated your question. So
there is no, so if you do Alexandrov curvature bounds and the convergence, then you still have the theorem that...
If a curvature bounded is smooth everywhere, but there are examples of a curvature is not bounded.
I see.
So it's not bounded. Maybe I'll give you an example in a moment. Okay. So this is a Hausdorff measure. Okay, so you basically count a number of, so you cover the ball by radius r, then you take a summation of this, take the infimum over the covers and so on. Okay, so it's a Hausdorff measure.
And it's clear at this point that the Hausdorff measure, the Hausdorff dimension of M infinity is n. Yeah?
Yes,
yeah.
yes, yeah. So n is a dimension start with. Okay, so okay, so I should say in general singularity happens. Okay. The general singularity happens is, for example, you take C2 quotient by finite group, by this group, the simplest one. Okay, so this is a singular space, and you can embed this into a complex analytically into C3 by taking all the invariant polynomials. Namely, you take suppose here is xy, okay, and this goes to x squared plus y squared and xy. Suppose this is UVW, So then it's a hypersurface. Inside here is a hypersurface, just u times v equal to w squared. Right? So this is the image C2. And you can take instead of here you take like sigma epsilon or x epsilon of uv. This is smooth, and this one all has a Calabi-Yau metric. Actually, it's a kind of scanning, it has a Calabi-Yau metric. So namely, it's a Ricci flat. So then you're scaling down. You scale down, try to pull everything back to origin. Okay, so this is holomorphic to x1 because you just do scaling. You replace the epsilon by maybe by square root of epsilon.
Mm-hmm. But okay. The hypersurface, it will still be smooth almost everywhere.
Yes. So in the limit, what I try to say, you scale this. Mm-hmm. So let's say you have a metric. Say I put this g epsilon. Okay. So then you take x1, maybe square epsilon inverse of g1. I could be right. I think it should be this way. Okay. So and the origin maybe some fixed some point. Okay, so this will converge to because you're pulling everything back to here, and you can imagine this metric at infinity is flat. I mean, let's claim that. Okay, assume that. So it's almost flat. So this back to this C2 minus sigma x0, which is this, and flat metric. Okay, this flat metric is just a quotient of flat metric here. So then this one has a origin is a singularity, is a cone. Okay, so you do have a smooth. So yes.
So when you put back the epsilon, you get epsilon g. Is that a claim or no?
This is actually yes. This is just x epsilon g epsilon. And that's right. Okay, but maybe this point may move a little bit because okay. So maybe I should put x epsilon here. Okay, but it stay in the compact set. So then this around same time, and I did with Kähler and coding, and myself, we noticed we had some curve. So if M is Kähler, GI is a Kähler Einstein. So namely, it's not only Einstein satisfies the Ricci curvature condition, it's also Kähler matrix. Then the singular set is codimension 4. 4 local of actually strictly speaking, there's a theorem here I state a little bit stronger than what I did with the coding. So it's actually due to Kähler and myself. So this is S is actually codimension 4. So and more recently, and Kähler is not quite related to what I'm doing, but I should mention it because this is a big, just a few 2-3 months ago, this or in the summer, so maybe longer than 2-3 months. So Kähler proved this is true for real, so you don't need a Kähler. This conclusion now is true for any Einstein metric. Namely, they really improved these things. Okay, so that here was a non-standing. It's a conjecture for quite a while. Okay. So that's about the general case we can do. Okay, so I will talk today. I will back here to say what we can do later, more. Okay. So what is things you expect? Okay. Actually, even in the 90s, Jeff and I, Kähler and I, try to do try to understand further the singularities. For example, so you can question is can we say more about the structure of S singular set? So this is called a singular set of M infinity. Okay, and for example, we expect, actually I guessed, is a S. So there's this S should be so write as a S0 and the union of S1. Okay, and maybe this S1 is so Hausdorff measure of n minus 4 S1 is 0. So it's and the top stratum. So this is a orbifold. So M infinity, this G infinity is a orbifold. Near S0. So by that I means near any point here it's just like here. Just except the group may be more complicated. It's a finite group, but maybe more complicated. But still, it's only singular is a finite caused by finite group quotient, which has a fixed point. Okay, so maybe I should say so. So near what I mean here is near each of these points here. Locally, there's open neighborhood such that it's a finite quotient of a smooth open set in Euclidean space. And the metric, and pull back to this phi cover, is a smooth metric. Okay. So that's called orbifold space. Okay. Any questions? Is that clear?
Does the conjecture also describe the cover in terms of coverings of the factors that go towards M infinity?
And which do you mean the tangent cone?
So
tangent cone is known. So.
But there's supposed to be a certain covering of S1.
So here I mean orbifold means the following. So for any, so this means for any point here, there is a neighborhood, okay, such that Ux is U tilde quotient by finite group. The U tilde is in the Rn.
So my question was whether there's also this conjectural description of U tilde as the Gromov limit of some coverings of some parts of the.
Yes, you can say that too. That's definitely. It's presumably when you take a covering, this singularity become it could be weaker singularity.
Yes. Does not have necessarily the flat metric here.
No, the metric is not flat. I haven't. So metric here is the G infinity. You pull back on the Ux, pull back to a not necessarily flat, to a smooth metric. On the U tilde. Okay, it's just like here. The G here down here is a singular, but on up to here is a smooth metric. Smooth metric. Okay. So this is the reason. Somehow the reason is true is the tangent cone like that. It was already proved in this theory we had.
But this is under the stronger assumptions of the Kähler coding.
This is yes, on the stronger assumption.
Conjecture. Yeah.
Yes, the conjecture, and if you only know a ratio coverage bounded from above, that's sufficient for this Kähler coding. Except here is not C infinity, it's just maybe C1 alpha.
But then also
also you expect that. You also expect that, yes. So because one evidence for that is for each point here, the tangent cone is like that. Tangent cone is Rn quotient by finite group. Mm-hmm. Okay, outside the set of measure 0, this is true. Of course, you can go further, ask what is the size of this set. That's become more technical and difficult. Okay, and also I should mention even Kähler proof the singular set is rectifiable. It has some structures. Okay, some actual structure. So but still this is not optimum. So what at least.
So does the Perelman stability theorem, does it hold in the setting? So if you assume that the limit is a manifold of the same dimension, then
if a is so Perelman theorem is for Alexandrov space, right? Mm-hmm. So it's in that case when the curvature bounded from below. It's if we assume there's also upper bound of rich curvature, then curvature is bounded, mm-hmm. then it does not have singularities. Mm-hmm. So you have it's a smooth. So the difference go from a curvature, boundedness of curvature to boundedness of rich curvature is if you bound the curvature, there's no singularity. Yeah. So but the rich curvature it does. So actually that's in some sense that's these are Einstein equation, solution of Einstein equation. That means Einstein equation develop some singularities, and it could be interesting. So then what we do here is so is for the are there any more questions? Because I want to say more about this structure. So if not, maybe I say so in this series, in this I guess last talk, in my last talk when I talk about this solution of some conjecture, I need I need this compactness theorem, okay, but in the end, actually we get much more than that. Okay, so that's what I first explained to you. So let me recall something we had before. Now, assume this is a say MGI Kähler law, okay? Kähler Einstein, say. For simplicity, or actually a lot of these things, actually my conjecture was proved for only for the Kähler matrix with rich curvature bounded from below now. But that's for simplicity, let's just do this. Okay? So then we want to say, we can say more. So first let me state the result, okay? So this is, maybe I explain to you, because otherwise you don't. So let me explain something. So since this is a Kähler manifold, so I know this is this GI locally is given by some Hermitian matrix, right? So it's given is given by its Kähler form. Kähler form. Okay, which is closed. D omega I is closed. So I know this is represents the Kähler class. Okay. So it's a cohomology class, closed, so-called Kähler class. Okay. Okay. So in the situation we are considering, we assume even further. Well, let's assume this is just coincide with the first term class. Okay, maybe it's normalizing to pi first term class. Okay. So then we know this is a curvature. This is given by first term class some line bundle. So this I have a line bundle. This time is I said last time is n of holomorphic determine the holomorphic tangent bundle onto M. Okay. So this is positive because it's represented by some positive forms. Okay. So there's old theorem of Kodaira. So which says choose any basis for for L sufficiently big, and any basis of H0 of M L, okay, is maybe I put M here to look like all the same. So gives the embedding phi into M. So right now I don't have any, it does not involve metric here. So n plus 1 is the dimension of this. Okay. Of course, depends on small n. And what's the embedding? Embedding just given by this. You look at the homogeneous coordinate, and suppose this is a base. This is a section in the basis. Okay. So if we recall, so this was known for a long time. So this is basically a corollary of some Kodaira vanishing theorem, or because of positivity. At each given point, you can use some tool, for example, L to estimate of D-bar operator, or use the algebraic called vanishing theorem to construct the sections with prescribed value at that point. Okay. So anyway, you have this. So it has nothing to do with the metrics yet. Okay. So now I want to, as I mentioned last time, I want to associate an embedding to a given metric. So now so this is what I did in a long time ago. So and refined by some other by Zerdish and Kähler and Ron and so on. Okay. So now I giving a omega I. So namely your GI I denoted by its Kähler class. So then I know this is giving this because this is represents a curvature. So there is a Hermitian metric. Hermitian metric, say Hi on this bundle, such that the curvature of this of Hi is omega I, because they both represent. So this follows from Hauge theory. Okay. So Hi is not unique, but unique modular multiplication by positive constant. Okay. So then with these things, you can define an inner product. So you look at the section, the Hermitian inner product. You look at the n, then you take Hi. And if you raise to m to get induce the metric on this, and S prime, this is Hermitian metric, and integrate against this omega n. And now this is you get embedding. So now you can choose now we choose orthonormal basis. Choose orthonormal basis. So let's see, Si. So this is orthonormal basis is again is not unique, but the unique modular compact group U n plus 1. Okay. So then what you do? So this depends on metric. So then you can do an embedding, say phi I. Given by this given by this orthonormal basis. M into CPN. Okay. So of course, image is a complex analytic variety. It's complex analytic submanifold, and this complex analytic submanifold is unique modulo this unitary transformation. But this is a compact group. Okay. So what we can know is since it's a limit, this is known because as a complex submanifold here is essentially defined by some polynomial as zeros of polynomials, finite many polynomials, and they also have a limit by taking subsequence. Okay. So the phi by taking a subsequence. So a subsequence. So maybe I will not make a subsequence of this phi I m converge to some m infinity. I put a bar here. So this is in the complex inside of Cn. This is as a cycles, as subvarieties, or as a cycles. As a cycles. Okay. So maybe I just assume this sequence does. Okay. So and this limit is unique modulo this. If you say you choose a different orthonormal basis, you will take a limit, and this resulting limit is only differ from this by unitary transformation, which will not affect, since this compact group will not affect the structure of this limit. Okay. So now we have two limits. One has nothing to do with the complex geometry. You have a Gromov-Hausdorff limit, which we already know some regularity things, and we don't know some regularity things. Right? So we know a large part of that is regular, and the singular set, we don't know much about singular set structure. So on the other hand, we have this complex limit. Okay, I know this is a variety. It's a variety, and the singular set is subvariety. Okay, but I don't know whether this has more than one component or not. For example. Right? But Gromov-Hausdorff limit has only one component. So it seems to be have two limits. Each one has its plus or minus. Okay. So in general, you can ask a question whether these two limits coincide. Okay. Since Kähler geometry means you have a Kähler condition since they fit a complex structure with a metric structure nicely. So we also expect this regularity theory. So the guess is so at least expect, okay, and now this can be proved. So this is m infinity. Okay, so this m infinity before is the same. Okay. So in the one-to-one correspondence of this.
So is there symmetric between this?
Yes, that's a good question. So right now you have a few things. First is space. Okay. So and you also say what's the natural space? You want to say this m infinity, the limit gives this identification. Okay. And moreover, the regular, even you have this identified, you still need to say singular set coincide with a singular set. Of this. Okay. So of course here is a complex analytic singular set. It's as a variety, it's as singularities. Okay. So this immediately says that first it says that this manifold, this limit, Gromov-Hausdorff limit, is a complex variety, and the singular set is a subvariety. And the metric, on the other hand, this one has a metric here too. It's a smooth outside symmetric here is smooth outside singular set of variety. So namely, it's smooth. Metric is smooth whenever the space is smooth. Okay, so and also actually recently, together with Tian and some algebraic geometry, we can prove using some things in algebraic geometry, which I don't think is necessary, but right now just we do that. This is also true. So namely, outside the codimension 6 subvariety, singular set is orbifold singular on the metric level too.
Codimension 6 or?
And complex codimension 3, real codimension 6. Okay, so it's once you know this is a variety, the singular set is stratified subvarieties. So outside codimension 6 is actually stronger than this. You know, the metric is orbifold metric. Okay, so this indicates one thing is and this at least this by identifying a holomorphic by identifying a metric limit with a complex limit, you can know much better about the singular structures. And actually, I expect you can understand the completed singular structures. But right now, only up to codimension 6. Okay, I see. So
it's math infinity. It's not an isometry. It's just when you take n to infinity, it's isometry.
M infinity is not isometry because it's just a one-to-one map.
Like this, when you take a big n to infinity, it could become an isometry? Yes. So once you prove this, the corollary is, actually I didn't pay attention to it, but indeed, yes. So that's from what the proof in the thesis is, as m goes to infinity, because this m infinity now this time depends on m, you pull back for this standard metric here, this homogeneous metric here, then you normalize, otherwise it's blows by everything. This converges to omega infinity. Let's say this d infinity. Okay, so this corresponds to g infinity I said before. I write in terms of forms now, okay, into Kähler form.
So what is known about this?
This is all known now. Now I explain to you how do you see that. Okay. So time goes on. Probably I cannot explain the role of a partial serial for proving that theorem, but at least I can explain to you this. Okay. So now let's see how we do it. Okay, how we do it. So this is a theorem now. So okay, and this is due to and independent myself. Okay. So the key thing is again this partial serial estimate I proposed before. And what we did here is basically to solve that conjecture. So then by some arguments I already knew and to derive this. Okay. So now let me go back to here. Okay. So Kähler theorem says so we can have one more. So take also a lot more bases here. We can define this a function called rho omega I, and which depends on m. And norm of hi. Okay. Take a square norm sum. Okay. And you can easily check this rho omega I is independent of choice of of hi, because I said this is not unique. It's unique only up to multiplication by positive constant, okay, and the basis. Maybe I used too much I here. Sorry, it's always the issue when you have a. So if you change orthonormal basis, obviously you don't change this sum. Okay, so it's actually a well-defined function. Only depends on two things. One is metric, one is your m. Okay. So what actually in my thesis I already know. The leading term is you can so A0 you can have an expansion. So this is a work of due to myself and Ron and Zerdich and Kähler. Okay, so you can start with m to n A1x. So this is a asymptotic expansion. So in general, you may not have a convergence. If a metric is analytic, it's a Paul series converge. Okay. Expansion. So namely, the expansion here means for any finite order term, you can have you can take a difference, and the difference is small, it's high order. Okay. So in fact, A0 is identical equal to 1. And A1x is a scalar curvature of your metric divided by 2, and so on. So it's like a hit kernel. Every coefficient can be computed in terms of curvature and derivative curvatures. So in fact, this I already proved in my thesis. This is you can expect. Why? Because if you integrate this, you can expect this must be 1 if it's constant. Because if you integrate this against the volume form, what do you get? Because each of these is 1, you just get n plus 1. But that's just h0 of m L m. And since you have vanishing theorem, all other things vanishes. All other things vanishes. So this is just Riemann-Roch. It's just Chern character of Chern character m times total class of m by Riemann-Roch theory. Okay, so in this particular case, it's just a warning because the choice of this degree. So it's a m times a warning because Chern character is m here. That's why you get this should be 1. So these things I defined here before, you can regard as a point-wise version of Riemann-Roch theorem in this positive case. So this is 1. So this means that this implies this rho omega I m and divided by m minus n, this goes to 1. Goes to 1. Okay. As m goes to infinity. Actually, this follows from here. If you check a potent dd bar of this, take a log of this, take a dd bar, you will get a difference of two metrics. Okay. So this actually follows from this. So follows from this for omega infinity. Okay, so this tells you at least for each fixed. So namely, for each fixed omega I, this m, this omega I m, it should be bigger equal to some maybe half of m n, and maybe bigger equal to some positive constant for m sufficiently big. So my guess is so-called partial zero, because, and I don't have time to explain partial zero. I can do that, maybe some people are interested. So the conjecture is this, I just, so for, there is a I, there's a, there is a constant C, depends only on a dimension, okay, and maybe a mu, okay, such that for any manifold of Gi, or maybe I put the omega I here to be Kähler-Einstein, to emphasize Kähler-Einstein, equal to mu omega I, and the Kähler class is inside of this. It can be more general, okay? And so it could be plus or minus of this. So lambda need to fix a class such that, so there are, maybe I put the k here too. All are positive, okay? Such that they are air, they are m, I goes to infinity. This is rho omega I, sorry. Let's put it this way. Since for all of this, okay, so any metric satisfies this condition such that we satisfy this, and there is a sequence go to that. This sequence may depend on this omega of m bigger equal to a Cm. Say, let's put it this way. Ck is here for k equal to mi. Okay. So there's a stronger version of that. So stronger version says there is a maybe k0 positive, the integer, such that the k equal to air k0. So star holds for k equal to. Okay. So this is a stronger version claim. Okay. So what I do here is actually you can interpret this as an effective version. Effective version of this effective version finite generators. Yes. Of a ring. So this is a ring, depends on air, m air. This is rings finitely generated. So that's known. Okay. So I say effective version of that. That means not only have finite generated and these curvature conditions, I want them to have a uniform generator. Is that clear? I didn't state it clear. So for each fixed m, this is a ring. This is the finally generated ring. Okay. So what's the difference here is now I consider a sequence of metrics here. This has nothing to do with metric. Now I want to include a metric structure. So if I have a family of metrics with these curvature conditions, these normalizations, this like, okay. So I want this function to be bounded from below uniformly. So maybe a little bit harder to now to understand why this depend on ring of finite. Maybe next time I say a few words about proof, then you will see why it is true. Okay, so maybe I say it here. So the ring, to prove this ring is finite general, the key things to prove what? To prove for M, so there is M positive such that the basis, so-called H0 of M Lm is base point free. Then by some complex analytical techniques, you can prove a ring is finite generated by this set of, by basis of this. Okay, so or by basis of, or by all the sections for this cohomology group with L m prime less equal to n. Okay, so it's based on free means you take a basis here. This is this is empty. This is empty. So your key point is because if it has a common zeros, if you find some other, you think this is a polynomial. You take other polynomials, you want to check this polynomial can be written as a finite generation sum of these given polynomials. It's tricky because then you need that polynomial to vanish into a certain order, right? But if a base point free is much easier to do, right? So that's a So here I just want to say more effective version. So it's if giving a metric, then also normal bases have a certain estimate from below. Okay. And it turns out to be important. So for example, this second coefficient can be used to check stability things, which in the GIT, which cannot be done by a previous method, by other methods yet. Okay. So maybe so this is so we can to prove this exactly by checking this to prove this conjecture here, okay. Conjecture here, and why is that possible? So if the conjecture is true, then we know this phi I, right? You define in terms of basis. Maybe my time is up. So maybe I say it because write is slow. So now if a conjecture is true, for each of these metric GI in the sequence, we take orthonormal basis, okay? And this orthonormal basis, by taking a sequence, this orthonormal basis, we have a limit, all have a limits, okay? And this limit has no common zeros by that assumption there, because this I mean, it turns out this is also uniform continuous function for each fixed k, okay? So then. If this has a limit, and the limit has no common zeros, then this phi I will converge to some map. Okay, and this map will give you this map, but still you don't know whether this map is one-to-one yet. But at least you first get a map. Okay, so then by using a L2 estimate, once you have a map, and you want to imitate how you prove a ring is finite generated, so-called using a Skoda technique to prove once you raising a pole of m, make m big enough, this will become embedding. So that's exactly like how you prove a ring is finite generated. Okay. So maybe I stop here. Thanks.
I
simple one. In your proof there, in analyzing the row,
Yes.
At the end, when you choose m going to infinity, it doesn't depend on the omega I, right?
Does not depend on.
Yeah, okay.
No, which one? Sorry.
There, down here.
So this C does not depend on omega I. It's uniform. Yeah, that's key.
And from there, it is reasonable for you to post the conjecture up there.
I'm sorry. Here, I guess I should. So here it depends on this. This C does not depend on I, but how big the M is may depend on I. So here I want to say this M does not depend on I. So there's a common M to realize this no bound. Okay. So you change I here, you may need a bigger M. So here it's not uniform on M. But this can be uniform. Okay. That's a difference. So conjecture here should be uniform everywhere. But you need a curvature condition. Otherwise, it cannot be true. Okay. So actually, the proof of this, proof of this. So essentially, to solve this conjecture here, is again to use this compacting theorem, so Kähler coding, and what I did with Kähler encoding. So using that, you can know the large part of that is okay. So then you again try to work using a tangent cones to say. So the compacting theorem is used to prove these things here, but the compacting theorem alone itself is not sufficient. You also need some other error to estimate from complex geometry. So then in the end, you get a better refined property of regularities. Okay. But this is it's not to solve this. You need a metric part too. Okay.
Other questions? Let's thank them.